Okay, we're going to continue lecturing here on kinetics. Last time we got into a couple of things regarding kinetics. Kinetics does involve obviously the rate of a reaction. So, it kind of gives us information on how fast or slow a particular reaction may proceed. We talked last time about one way to figure out sort of what's happening is what is referred to as the rate expression. And in general, the rate expression is really helpful because it does allow you to figure out in a particular reaction how reactants are changing, how products are changing over time, or really the average rate over a reaction. And that is, if you remember, we do want to take into account the coefficients when we do it. So we could write a rate expression minus 1 over A, change in the concentration of A over the change in time. And that equals minus 1 over B, change in the concentration of B over the change in time. A couple of things about that. Remember that the negative is because the reactant should be decreasing with time. So we do expect it to basically changing negatively in a sense as it's going down. 1 over the coefficient, as we talked about, will take care of all the stoichiometry, the mole-to-mole relationship that you need to do in a calculation. By doing that, we get to our product side. It works the same way, except there is no negative on our product side. And again, that is because we would expect our products to start to increase with time as this reaction proceeds. The useful thing of this is, as we talked about, that you pretty much can figure out how anybody is changing in a reaction as long as you know really one piece of information. So maybe you know the average rate, maybe you know how a specific reactant or product is changing with time, you can figure it out. Again, the negative here, as we also talked about, important because technically when you do the change in concentration for a reactant, your final concentration should be less than your initial, which will give you a negative number. And again, those two negative numbers will turn your rate or your average rate for the reaction into a positive number, which is ultimately what it always should be. So remember that the average rate for the reaction should be a positive number. Individually speaking, for reactants, you can have a negative rate, right? Because it's decreasing with time. Or individually for products, you should also have a positive rate as it's increasing with time. Any questions on any of that there? We finished up also talking about the rate law, which does take into account only reactants. And it basically has sort of a form like this. The rate is equal to K, A to the X, and B to the Y. And here, the little k is the rate constant. And remember, that is sort of the constant value, if you will, that you get for a particular reaction. It also really does sort of give you an indication of how fast or slow the reaction is occurring. Sort of a larger rate constant, then it's going to occur a lot faster, kind of a slower one. Our lower one is going to occur a little bit slower. As we also talked about, these guys up on top are what are referred to as orders. And they're sort of the proportion at which you need each of those reactants basically to achieve a specific rate. The sort of useful application of it, as we talked about, I think at the very end last time, is, if you know the orders, you could, if you wanted to do something with the actual reaction, maybe you wanted to slow it up, maybe you want to speed it up, you can play with the concentrations, and one reactant may have a greater effect than the other. And as we saw at the end there, you could have, again, a reactant that is to the 0 order, which really means it will have really no effect on the actual rate of the reaction. So, you could kind of play with the concentrations. If you sort of practically wanted to either speed up or slow down the reaction, you could pick a specific reactant or maybe a little bit of both to kind of achieve sort of how fast or slow you want the reaction to occur. Those things are not the coefficients in the balance equation. They are found experimentally, and that's where we're going to pick up here. Basically, you do need to actually calculate it from experimental data, how to figure out the X and the Y or the orders for each of them. If you add up each of those orders, you can get the overall order of the reaction. And that is found by simply adding up basically the individual orders for the reactants. Usually it is just reactants in a rate law, no products. So it's only really reactants involved. Any questions on any of those things there? So typically speaking, what we will see here in just a second, but typically speaking, what we are given in terms of data is we are usually given like the concentration of a couple of reactants in a table. We're usually given what is sometimes referred to as the initial rate and molarity per second. And there's usually several entries in a table. And there's a couple of ways you can approach these problems. You can sort of analyze the table and figure out, as you change the concentration, how does that affect the actual rate that you see? Most people are probably best off sort of taking more of a mathematical approach to sort of solve for the orders. And we could do this by just taking a simple sort of formula where we take rate 2 divided by rate 1 is equal to Ka to the x and b to the y divided by Ka to the x and b to the y. So let's talk about really what each of these things are. These are really two entries in the table. When we say rate 1 and rate 2, it doesn't mean you got to grab the first one and the second one. What we're looking for when we sort of analyze the table is we want its math. So we want less unknowns, right? So we really want one unknown. So typically when you look at this table, you should be able to find two entries in the table where one of the concentrations remain the same. So for example, let's just say this guy is 2 molar, this guy is 2 molar, this guy is 2 molar, and this guy is 4 molar. So when we look at this table, the concentration of A is basically the same. The concentration of B varies. And that's really what you're looking for when you sort of attack a table like this. And again, it could have 3 entries, 4 entries, 10 entries, but you're basically looking for where you could keep one reactant constant, the other one should vary. And you would have rates that are associated with that, so for example, we'll just say that this is 6 molar seconds, and we'll call this 12 molar seconds. So what we would do is if we chose these two entries here, typically speaking, you want to kind of take the larger rate up on top. And you don't necessarily have to do that, but a lot of times it will give you nice whole numbers or kind of easier the math to do that way. So for example, what I would do is if I was going to take those two, what I would want to do is take all information for entry number 2, since it does have the larger sort of rate, and I'm going to put that across the top, which means in my example here, that would be 12 is equal to K. The concentration of A here is 2 to the X. Concentration of B would be 4 to the Y. And that is basically everything that comes from entry number 2. I would do the exact same thing for entry number 1 here. The rate is 6 for that guy equals K. Again, the concentration of A is 2, and the concentration of B is also 2 in this case. At this point, what we have is really sort of one unknown. We could do some math. 12 divided by 2, 12 divided by 6 is 2, right? This is the rate constant on the right, on top and bottom. Although I do not know what the rate constant is at this moment. Is it a constant value? Hence the name rate constant, which means the rate constant on top and the rate constant on bottom, although I don't know what it is, should be the same number, which means technically speaking, they cancel, right? This is the order with respect to A on top and bottom. Again, at this point, I really don't know what that number is, but because it's the same reaction, it should also be the same number, which technically means that's basically the same on top and bottom, and those guys will cancel out as well. When I take 4 divided by 2, I end up with 2 to the Y here, right? When I do the last one. Now we can solve this by easily seeing that Y should equal 1, yes? 2 to the 1 is 2, right? And it gives me 2 equals 2 on both sides. If you was not a pretty number, how could you solve it? You could take one way is you could take the natural log of both sides. When you take the natural log of the other side here, that brings the Y to the bottom, would equal the natural log of 2. You would divide the natural log to both sides, and you would end up with 1. So if you don't get a really pretty number, you could actually take the natural log of both sides and divide them, and you'll get a better number, maybe closer to a whole number, stuff like that. But again, in a lot of cases, if you kind of take that larger rate up on top, you'll kind of get more really whole numbers. If you do it the opposite way, you will get decimals, and then you probably need to do the natural log of both sides and divide it out. Any questions on that? By doing this, what this basically would tell us is the order with respect to B would be first order. What we would then want to do is go back to our table. And what we would then want to do is, because we held A constant the first time, we would want to find 2 entries in the table where B remains constant and A varies, and do basically the same calculation. And that is basically probably the best way to sort of approach these type of tables. Any questions on that there? All right, so let's take a look at one here and see what you end up with. So let's say we have this reaction. This is the data. So why don't you give it a try here? We want to calculate the orders. We want the rate law. We want the orders, the rate law, the overall order of the reaction. And we would like the value of the rate constant when it's all said and done. So why don't you give it a go and see what you come up with. So look at this table. Again, you're looking for 2 entries where one remains constant, the other one varies. Do the little math we just did on the previous page there and see what you come up with. Let's take a couple minutes and we'll talk about it. Take a look and see if you're on the right track here and how you're doing. So again, we can start with just sort of like the generic rate law here. So if we look at this equation, we got the rate should equal K, and that's a lowercase k, F to the X and ClO2 to the Y. Remember, it is only the reactants that are involved here. Again, this is a very typical type table that you're given. So we want to analyze the table. And again, we're looking for really one reactant to remain constant, the other one to vary. And by the way, obviously, if you had more than 2 reactants, you would want to keep 2 constant and only vary 1 at a time, so you don't get too many unknowns. By looking at this, we could clearly see 1 and 2 will achieve that for us. The F2 concentration remains constant, while the ClO2 concentration varies. So if we look at experiments here, 1 and 2, and again, in this case, you don't have to do this, but it sometimes makes the calculation a little bit easier. I'm going to put the larger rate up on top. And again, that means I'm going to use everything from experiment 2 and put it all the way across the top on that formula that we just looked at. So that would give me 4.8 times 10 to the minus 3 is equal to K concentration of 0.1 to the X, concentration of 0.01 to the Y. And that was not right. So that is 0.04 there would be the right one to put in there. So putting everything from entry number 2 there up on top. Now entry number 1 will go on the bottom. I'll try better on this one. 1.2 times 10 to the minus 3. Okay, this is going to be 0.1 to the X. And that should be the 0.01 that I was looking at just a second ago. Any questions on that? At this point, we could do our math. So dividing here, that is going to give us a 2. Again, same reasoning as earlier. Our rate constant will be the same on top and bottom, which means they cancel. Here, the order X would be the same on top and bottom. So since the concentration is the same, they would also cancel. Taking our 0.04 divided by 0.01 here, that is going to give us a 4 on that side and a 4. I'll get that math right. I know I should grab a calculator. It's all right. So that is 4. Just want to make sure you're paying attention. And that obviously gives us 4 divided 4 is equal to 4 in this case. Yeah, so 4.8 divided by 1.2 is 4. And that gives us 4 is equal to 4 to the Y. Again, you could clearly see in this case that Y is equal to 1. Again, if you weren't really sure, you can take the natural log of both sides and divide. So what I mean by that, you take the natural log of the 4 on the left, divided by the natural log of 4 on the right, and that would equal Y. Any questions on that, except for my really bad math right there? All right. Now that we figured out the order with respect to ClO2 is 1, what we now want to do is go back and find 2 entries in the table where we are going to be keeping the ClO2 constant. And it looks like if we do entry number 1 and entry number 3 here, that will achieve that for us. So looking at experiments 1 and 3, again, same here. I'm going to take number 3 up on top since it has the larger rate, and not going to screw it up this time. 2.4 times 10 to the minus 3 equals our K 0.2 to the X, 0.01 to the Y. Again, all those numbers come from the third entry in the table. We're then going to divide it by the first entry in the table, which is 1.2 times 10 to the minus 3, our K, our 0.1 to the X, and obviously our 0.01 to the Y. Now I got my 2, I hope. There you go. Again, our K is going to cancel. In this case, this will give us a 2 when we do that, and these guys will completely cancel, which means we get 2 to the X in this case. X would equal 1 when you solve it. Any questions on that so far? What we have now just done is using the experimental information. We have figured out the orders with respect to each of the reactants, which means we could technically write the completed rate law at this point. And the completed rate law would be the rate is equal to K F2 to ClO2. Much like most things in chemistry, we don't need to put the ones up there on top, but it is assumed that it is 1. That means that the overall order here of this reaction would be, 1 plus 1 would be second order. And again, we get that basically from adding each of the orders that we calculated there. At this point, we've solved for the completed rate law with the orders. We got the overall order. The last thing that we want to do is figure out what is the actual value of the rate constant. And we could do that because we now have the completed rate law. So that means we can now take that rate law and actually solve for K. And if I take this rate law here and solve for K, K would equal the rate divided by F2 divided by ClO2. So all I'm doing is taking that rate law, rearranging it, and solving for K. Now the question is, where do I get those numbers from? And the answer is you get them from the table. So you could choose any entry you like. You could choose entry number 1. You could choose entry number 2. You could choose entry number 3 if you like. You just can't mix and match, so you got to choose one entry for everything. But they all should give you the same value because, again, K is a rate constant, which means no matter which one you take, they should end up with the same value. So I'm just going to take number 1 there. So for number 1, the rate is 1.2 times 10 to the minus 3 molar seconds divided by our F2, which was 0.1 molar, and our ClO2, which was 0.01 molar. And if we do all that good stuff there, we end up with 1.2 as our rate constant. What would be the units at this point? A molarity up on top and a molarity on the bottom cancel. You end up with 1 over molar seconds. Yes. And those units are actually the correct units for a second order reaction overall, 1 over molar seconds. One of the things we will learn is the units of the rate constant will tell you what type of reaction you're dealing with, and that is specific for a second order reaction. Yeah. You would have to square it, yeah. So if, for example, just say, for example, F2 was an order of 2, when you would come down to where I just did the 0.1, you would have to square it at that point. Yeah, yes, carry those out. Because basically what we did on the bottom is really based off of your rate law. So if you do have those guys, they would carry through. Other questions? Okay. So this is a very common way that you can show how to get the orders and all that mathematically. You can do it just by looking at it and going, we double the concentration, the rate doubles. It's kind of proportional. If you choose to do it that way, you got to write it or something, but I would probably do the math way would be a good way to show your work, I guess is the best way to say that. So rate laws, as we've been talking about, are always determined experimentally, which means you will always have basically tables of these type of problems given to you. We always talk about only really the reactants in our rate law, since we have the reaction really going to the product side in the forward direction. So that's really the most important. The order, again, is not from the coefficients, and it is found experimentally. Sometimes, obviously, it does match the coefficients, but not in all cases. As you can see here, we had a coefficient of 2 and obviously an order of 1 in this particular case. All right, so why don't you try this one? The rate equation or the rate law for this reaction has a rate that is 6.6 times 10 to the minus 5 when the concentration of NO is 1 times 10 to the minus 6 and O3 is 3 times 10 to the minus 6. What is the rate constant? Okay, so in this case, it actually gave us the rate law. So all we have to do really is rearrange it. So we're going to take these guys here and divide it to the other side. That's going to give us that K is equal to the rate divided by NO, concentration NO3, which they also provided for us. So that would give us a 6.6 times 10 to the minus 5 molar seconds divided by our NO there, which is 1 times 10 to the minus 6 and our 3 times 10 to the minus 6 molar. In this case, it gives us there. 1, 2, 3, 4, 5, 6, 7. Looks like perhaps 2.20 times 10 to the 7 in this case. In terms of units, again, molarity on top, molarity on the bottom cancel, and that leaves us 1 over molar seconds, which again is the same type of units that we saw previously for the same or similar second order reaction. Any question on that there? Now, the sort of answered question, or just to look at sort of what would be, let's just say that the rate law here was K NO squared, and this guy was O3 to the 0 order in this particular case. Again, when we would go to solve this, the K here would equal the rate divided by NO squared, O3 to the 0 order. When we do that, again, we would put in our numbers divided by our NO, which is our 1 times 10 to the minus 6 molars, and we would square it, which was the question. And over here, we would have this guy, which would be to the 0 order. As we talked about, saying to the 0 order will equal 1, right, basically. So that will sort of cancel out. And we would need to, in this particular case, we would need to take 6.6 to the minus 5 divided by 1 to the minus 6, and we would need to square it. And this would give us, in this particular case, 6.6 times 10, 1, 2, 3, 4, 5, 6, 7 as well. 1 over, in this case, molar seconds as well. Again, we would get molarity squared on the bottom, right? And we lose 1 from the top, and we would be left with 1 over molar second. So the answer to the question there, again, you do want to take into, obviously, the orders. If they're not 1, they will not always be 1, obviously. So whatever they do when you go to calculate K, you do want to take those into account. Any questions on that there? Okay, so let's try another one here. Let's try this one. Let's do the same thing. We want the completed rate law with the orders. Let's also get the overall order, and let's also get the value of the rate constant. All right, take some time and see what you come up with. So getting one approach is the same way. We could just start with sort of the like to call the generic rate law. So the rate would equal K in this case, S2O8 2 minus to the X and I minus to the Y. Again, we're going to look for where we're going to keep one of them constant. So looking here, 1 and 2 should achieve that for us for the first guy. That would vary the I minus. So looking at experiments 1 and 2 here. Again, I'm going to go with experiment 1 on top because it does have sort of the larger rate. And then just putting in my numbers for everybody else there. I think I actually copied it right. So that's a progress there. Then going to put number 2 there on the bottom, all the way across 1.1 times 10 to the minus 4 RK. And again, that's 0.08 to the X, 0.017 to the Y. In this particular case, when we divide, that's going to give us a 2. Again, our rate constant will cancel. This guy, which we really kept constant, will cancel as well. When we divide that, I believe that will also give us a 2 to the Y. Again, Y here would equal 1, which is our order with respect to I minus. Any questions on that part of the calculation there? We then will go back to our table looking for keeping the I minus constant, which looks like it is experiment 2 and 3 will do that for us, keeping that guy constant. So taking those guys into our calculation here, 2 and 3. Again, I'm going to go with number 3 up on top since it does have the larger rate. So that's going to be 4.4 times 10 to the minus 4 equals our K 0.16 to the X and 0.017 to the Y. Now putting number 2 on the bottom there, 1.1 times 10 to the minus 4, our K 0.08 to the X, 0.017 to the Y. When we do our division here, that is a 4, I hope. The K's cancel. These guys will also completely cancel. Doing the math on this guy, basically 16 divided by 8 is 2 to the X. In this case, so you could probably just visually see it, that X would equal 2 in this case. Again, you can take the natural log of 4 and divide it by the natural log of 2, and you should hopefully get 2 at that point. Any questions on that so far? Yeah. In this particular case, the way I wrote it, X is in respect to this guy right here. Yeah. The S208. Yeah. You can use any letters you want, so whatever you kind of do. But usually most people use X and Y, maybe Z if you need. And again, X is usually the first guy on the table or in the recur action and stuff like that as you go through. Other questions? Okay, so now that we got the orders, we could actually write the completed rate law, which in this case would be the rate is equal to K, our S2O82 minus, and that would be to the second order. And then our I minus here to the first order. That would be the completed rate law right there with the orders. That would also tell us that the overall order here would be 2 plus 1 would give us third order in this particular case. And the last thing that we're going to do is we're going to solve for the value of the rate constant. So I'll flip a page here, but I'm going to take the rate law here and solve for K. And when I do that and solve it for K, I get that K is equal to the rate divided by S2O82 minus squared, I minus to the first. Again, as I mentioned previously, you can pick any entry you like in this table to solve for K, and it should come out the same. So here I will take, why not? I'll take the second entry here and put it in. So that is 0.08 and 0.017. Squared and 0.017. And I believe that was a, if I go back, maybe keep putting lines on the paper. There we go. It is 1.1 to the minus 4. 1.1 to the minus 4. And if we do that there, it looks like we will get 1.1 to the minus 4 divided by, again, here we would need to square that 0.08 and divided by 0.017, I believe. And I think I get a 1.01, if I'm not mistaken. And at this point, in terms of units, they would be what here? Yeah, molarity here will cancel, and that will leave us 1 over molar squared seconds in this case. Again, this guy's being squared, and we got 1 down there. Again, different than what we saw for the units for a second order, right? So again, the units that you see associated with the rate constant will kind of give you an idea as the overall order of that reaction. Yeah. It does. I probably messed it up here, but I think we had 2 on everything, so probably should or even we had 1 maybe with the 0.08. Was that one just 1 in that table? You should try to get it, but it's somewhere in that 1.0, I think. Yeah. Other questions? Now, the value of the rate constant does give you an idea, again, how fast or slow it goes. Obviously, this would go a lot, probably slower reaction than the one we saw on the previous one that had like a rate constant of like 2 times 10 to the 7, right? Or whatever it was there. So it does give you that sort of idea how fast or slow it's occurring. Any questions on that there? Okay. All right. So why don't we do this one here and see what you come up with? All right, let's take a look, see how we're doing. So same approach here. We're going to go with the rate is equal to K. I'm going to go with NO2. I'm going to call that X, and CO, I will call it Y. So in this particular table, there's actually 4 entries. And like I said, you could have a lot of entries sometimes. There are, and for example, to keep CO constant, we could obviously do that with 1 and 2 will achieve that for us. We could also do 1 and 4 if you wanted to. You could also do 2 and 4 as well. They all will essentially give you the same sort of end result there. So let's take a look at experiments 1 and 2 here, and that should keep our guy constant. I'm going to go with number 2 up on top since it has a little larger rate there, and that's going to give me 0.0082 equals our K, and it looks like 0.2 to the X and our 0.1 to the Y. And number 1 on the bottom there, 0.0021 or K, 0.1 to the X, and 0.1 to the Y in this particular case. Doing a little math here, we don't get really pretty numbers perhaps on this one, 0.0082. And because it is experimental, that does sometimes happen. So you probably lay up something like a 3.9048 if you take a few numbers. On this side, we get some K's to cancel. Obviously, this guy's going to completely cancel. That's going to leave us 2 to the X. Again, here you can take the natural log. The ln of 3.9048 is equal to the ln of 2. When you take the natural log, the X comes down. And then you can divide the natural log to both sides in that particular case. So if we do the natural log here, and we divide it by the natural log of 2, we end up with an X value in this particular case of like 1.97, which is pretty close to 2 in this case. Yeah. Any questions on that there? By the way, if you did experiments like 2 and 4, if I'm not mistaken, I think you do get like an X value of about 2. And I think if you did experiment 1 and 4, I think you get like a 1.98. So all of them pretty close to 2. Again, no matter which one you choose, it gets you pretty close. And you can round in this particular case because it is sort of experimental. Any questions on that there? Yeah. I would probably, especially if it's an experimental sort of situation. I'll be honest with you, a lot of textbook ones that you do will probably come out pretty darn close to a whole number. They don't have to actually be whole numbers, but you should probably round to the nearest whole number would be a good idea. Yeah. All right, so again, no matter which one you sort of chose there, you would end up in that 2-ish range there for our order for, that was for NO2. We then want to go back now and keep our NO2 constant, which looks like in this case, we only really have 2 options here, which are here, 2 and 3. We'll keep that guy constant. So we'll go here to the next one. And what do I got there? So it's they're pretty darn close. So 0.008, we'll do number 3 on top. So 0.0083, I think, is equal to K. And we got 0.2 and 0.2, so that's good. So 0.2 to the X, 0.2 to the Y. And coming back, go back. The other guy 0.0082 and 0.1. And 0.1 here. In this case, again, not perfect, but pretty much 1 happening there, I'm assuming. So just over 1, like 1.01. Again, these guys are going to cancel. Those are going to cancel, going to give us 2 to the Y in this case. In this case, 2, the Y would equal, Y should equal 0 in this case, right? Again, if you took the natural log of 1, that's going to give you 1.01 gives you 1.2, then divided obviously by the natural log of 2 gives you there 0. So this guy should equal basically 0. That gives us a rate law of K is NO2, and that was squared, right? And this guy was, what was the other guy? It was, what was the thing there? CO, thank you. CO to the 0, which you really don't need to include in this case. You could really, if you want, just write the rate is equal to K NO2 squared in this case. Question on that one there. That means that our overall order here would be second, right? 2 plus 0 gives us second order. And in this particular case, we would be looking at a K that would be equal to the rate divided by really NO2 squared in this case. And again, we could choose from any one that we want. So might as well just go with the first one. That's 0.1, 0.1, and 0.0021. 0.0021 molar seconds, 0.1 molar squared, and obviously we don't need the other guy. And that gives us a rate constant of, looks like 2.1 times 10 to the minus 1 units here. Basically, one of those would cancel 1 over molar seconds in this case, or you could do molar like that if you like as well. Yeah. Question on any of those spots there? Yeah. Yeah. It truly doesn't matter. If you're asking, does the first one always has to be, X? It really doesn't matter as long as you know which one it is. You can use any letter you want, and you can really do any one in order. Sometimes people go by the equation and just call it that, based on how it's written in the equation. Some people go by the table as to which one's first in the table and stuff like that. So it doesn't really matter as long as you know what it is, because in the end, you're going to write a rate law that looks like this. Yeah. where you would not really include numbers, but you would include what it is with the order associated with it. So as long as you keep track of which one goes with which, it should be okay. Yeah. It's because of the units. So if we look at just the units of the final calculation, I think is what you're talking about right here. Yeah. So the final calculation, if we look at the units, what we have up on top is molarity divided by seconds. And then we basically have molarity squared on the bottom, which means the molarity up on top will basically cancel out one of those molarities, and that will leave us 1 molar seconds basically as to what's left over. If we look back at the previous one, which was this one here, I think, right? If we just look at the units, we had molarity per seconds up on top. We had molarity squared times another molarity here. So what happens here is this molarity and this molarity will cancel, leaving us with the 1 molar squared seconds in this case. Yeah. Yeah. Other questions on that? Okay. All right, why not one more just to make sure. Okay, let's take a look here. We're getting to the end. We'll start with our same approach. Our rate will equal K NH4 plus to the X and NO2 minus to the Y. Again, here we have multiple entries in this table, so we could choose whichever ones. Just quickly looking here, number 1 and number 2 looks like we're going to keep this guy constant, so we might as well start there. So experiment 1 and 2. I'm going to take the rate there for number 2 up on top. So that's going to be 32.3 times 10 to the minus 7. Don't forget to look at the table there. If you miss that, you'll be okay here, but not so good when you calculate the rate constant later. So make sure you always look at those tables. This would be K times 0.2 molar to the X and 0.2 molar to the Y. 0.02 molar. Now taking our 10.8 times 10 to the minus 7, our K 0. I keep messing that up there. I'm sorry. That's a 6, right? There we go. Thank you. So 0.06 to the X on top, 0.2 to the Y. It's when you're getting old, you're looking like this far away from it and you still can't see the numbers. That's bad. All right. So stick in the right numbers here. We'll go with 0.02. That seems right to the X and 0.2 to the Y. All right, so we're going to divide that there. 32.3 to the minus 7 divided by 10.8 to the minus 7. That's going to give us really like a 2.99, which you probably could call 3 if you like. That is going to cancel. That is going to completely cancel. And that's going to give us a 3 to the X, where our X here should equal 1 in this particular case. At that point, we will try to keep the guy on the left there constant, which looks like it is experiments 3 and 4 will do that for us. So experiments 3 and 4. Here we will go with 21.6 times 10 to the minus 7 up on top equals our K. And we'll try to look at the right number there. 0.2, I think, and 0.0404 to the Y. Coming across on the bottom there, we will go with 10.8 times 10 to the minus 7, our K, and 0.2 to the X, 0.202 to the Y. Again here, maybe not the perfect whole number, but maybe we'll be okay on this. 21.6 to the minus 7 divided by 10.8 to the minus 7. Going to give us actually a 2 here, so we're good. That is going to cancel. That's going to completely cancel. And then obviously we're going to yield us a 2 to the Y on that side. That's going to give us a Y that is equal to 1 in this particular case. Any questions on that calculation there? other than I missed the 0 there, but that makes it better. There we go. So 0.0202. At this point, we do have the completed rate law. Too many numbers to this. NH4 plus and our NO2 minus, it looks like. Running out of room there. The overall order here would be second order, as it's 1 plus 1, right? Gives us a second order sort of guy. At this point, we can't solve for K. So let's squeeze it up here. K would equal our rate divided by our NH4 plus and our NO2 minus. Again, this would be the case where if you ignored that times 10 to the minus 7, you are obviously going to get the wrong answer, because this is really the other part. You'll come out okay. You'll come out the same, but you definitely don't want to ignore it there. So that will give us, we got there, we'll go 10 to the minus 8 times 10 to the minus 7 molar seconds. Let's come back. Come here. Go back. There we go. 0.02 and 0.2. All right. 0.02 and 0.2 molar equals K. Again, here, molarity and molarity will cancel each other out. That will get us looks like 2.7 times 10 to the minus 4, 1 over molar seconds in that ballpark. Any questions on that there? All right, we've done a lot of examples of these. You should be professional. So these are obviously things that you need to calculate based on the data that's given to you, the rate law with the orders, the overall order, and the value of the rate constant. Any questions on any of that?